Welcome to this course on algebraic geometry and commutative algebra. In the last couple of lectures we have been studying integral extensions, and yesterday we were trying to prove the theorems of Cohen-Seidenberg. Let me recall briefly what we are trying to do. So we have a ring extension A contained in B. This is extension of rings. And we are assuming, suppose that B is integral over A, that means that is every element B in B is a 0 of a monic polynomial in AX. Coefficients are in AX and coefficients are in A, and the polynomial is monic and B is a 0 of that polynomial. Then we say B is integral over A, and B is integral, capital B is integral over A means every element of capital B is integral over A. And in this case we are trying to study. So this extension will induce a map on the spectrum level, spec B to spec A. This map is so this is, if you call this inclusion as I, this is I star. This map is any prime ideal P prime in B, that is mapped to, just pull back that I inverse of P prime. This we have denoted A intersection P prime, and we have checked that this is a prime ideal in A, and lying over theorem says that this map is surjective, that is given any prime ideal in A, whether it is coming from some prime ideal in B. That is what we wanted to prove. And yesterday what we proved was, if you take look at the maximal ideals SPMA, this is the set of maximal ideals in A, and then SPMB, this is contained here. What we checked, that is, if some M prime, then M prime intersection A, this is indeed maximal ideal, and if this is maximal, if and only if this is maximal, we have proved. So in any case this I star will induce a map here. This is a restriction of I star to the maximal spectrum of B. This we proved yesterday. This was precisely, so this is belongs here, if and only if this is what we proved. This was what I called it statement 1, and that followed from the fact that if you have extension of integral domains, and if it is integral, then one A is a field if and only B is a field. From that this followed easily. And now today I want to prove that the second statement. So this is what we want to prove. This is also called lying over theorem. That says that for every P in the spectrum of A, there exists P prime in the spectrum of B such that P prime lies over P. That means If I contract it to A, I get P. Then in this case we say that P prime lies over P. This is equivalent to saying, so I will write on the next. Equivalently, the map I star from spec B to spec A, P prime going to A intersection P prime is surjective. This is what we have to prove. All right, before I prove that, I want to discuss how many, not how many, but what is the relation between the elements given P. So, given P in spec of A, I want to know, is there a containment relation between the elements in the fiber over I star. So, that I am making a statement. So, before I prove that also, I want to set up some notation. So, given any P in spec A, we have this A to B, this is inclusion map I, and then I localize this A at P, A localized at P. So, remember A localized at P is by definition, take the complement of P, A minus P, and take the inverse of that, in S inverse of this. This is my set S. This is multiplicatively closed set because P is a prime ideal, and we look at this ring, and then B is a modulo over A. P is an actually algebra over A, but in particular modulo over A. So, I can also localize that B at the multiplicatively closed set this S. So, this is S inverse of B, this is S inverse of A, and this is the natural iota map, and this is the also iota map. This S is also multiplicatively closed in B because it is multiplicatively closed in A, and the universal property of the localization will tell us that there is a unique ring homomorphism which makes this diagram commutative. So, there exists unique, in fact we can tell what is the definition of this. So, what will it do? Any A by S, where should it go? So, that dictates you A by 1, if it was S is 1, then A goes to A by 1 goes to where? It should come this way. So, A goes to A under inclusion, and then that will go to A by 1 only. So, this is going to if you like iota of A, I star A, not I star, I inclusion, this is A is here, map it to here, IA, and then map it here. So, this is this. But because we are identifying this A with the subring of B, this is same as A by S. So, this is the natural map, and this diagram is commutative, that is because of the way we have defined, and also it is a ring homomorphism, that is also clear by definition. So, now the observation I am saying is, if A is integral, B is integral over A, if B is integral over A, then S inverse of B is integral over A, integral over S inverse A. This is very simple because you take the you have to show that every element here satisfy a monic equation or S inverse A, but take that element and it is of the form B by S, where S is in S and B is in B. I am checking that every element here is integral over S inverse A, but now look at that B. This B is integral over B is here. So, B is integral over A means there exists a monic polynomial. So, it will be like this: B power n plus A power n minus 1, B power n minus 1, etc. plus B A1 B plus A0 is 0, and with the A0 coefficients A0 to An minus 1, they are elements in A. Now, this is an element in the ring B. This is 0. This is 0 element, but now I want to read this in S inverse B. So, it will continue to be 0. So, that means take its image in S inverse B, it will be B power n plus An minus 1, B power n minus 1, etc. plus B A1B plus A0 divided by 1. This is also 0. But if this is 0, then I can further multiply up and down by S, that will also be 0. Not only that, I want to write the denominator S power n and absorb it here. So, this equation is same thing as up and down multiplying and adjusting the thing. This is B by S power n plus An minus 1, and now you keep it here whatever you need to, and remaining part you can absorb with that coefficient A. So, this is 1. So, I will write one term at least here. So, B power n minus, so S, not S, B by S power n minus 1. So, I accounted for B power n minus 1, I have accounted for this, and this is S power n minus 1. So, I have to still, so that S I will absorb it here, plus so on. So, here it is A1 by S power n minus 1 B by S plus A0 by S power n, and this will continue to be 0 also, because I have not done anything, I have just adjusted S, but from here I multiplied up and down by S power n, and then it is this. So, this is a monic equation, coefficients are in S inverse A, and it is an integral equation for B by S. So, we have proved this statement. Now, let us come back to the proving that what I want to prove the following statement. So, if P prime and P double prime, there are two elements in the spectrum of B with suppose they lie over the same P, that means P prime intersection A and P prime intersection A. There are two prime ideals in spec A, because they are contraction of the two prime ideals, and suppose they are equal, that means both these prime ideals lies over the same prime ideal P. Let us call this as P. P is by definition this. If they lie over the same P, usually such a diagram is drawn, then they are equal, P prime equal to P double prime. So, this simply means, so I will write in the bracket what does this mean. So, this means that for every P in the spec, the fiber that is I star inverse of P. There are no containment relation. Fiber has no two elements which are comparable with respect to the inclusion. That is what it means. Proof is very easy, as you will see. So, proof of this statement. So, I want to prove that if they lie over the same. So, now it is better to draw a diagram, I think. So, B is here, A is here, and there are two prime ideals here, P prime and P double prime. They are prime ideals here, and they are lying over the same one, P. The prime ideal here. And I want to prove that they are equal. And containment I forgot. So, if these are contained, so here also these are contained, then what do we want to prove? To prove P prime equal to P double prime. This is what we want to prove. This is contained here. Alright, now let us see. So, what do? I want to localize this. So, let us take S equal to A minus P and localize this. So, from here you pass on to the localized ring A localized at P. From here you pass on to the ring B localized at P. Remember, this may not be local, because P you have only localized this B at S of A minus P, and this is not an prime ideal in B. This was it here. So, this ring is local ring with maximal ideal PAP, which is the image of P. So, here the ideal P, this will go to the PAP. And this is the unique maximal ideal of this local ring. This is what we have done it in the localization. Now, here we have this map. Now, what happened here now? When you pass on these prime ideals to this localization, first of all, they will be a proper ideals here, because they do not intersect with this S. Because they are lying over P, means that P prime intersection S is non-empty, is empty, and P double prime intersection S is also empty. So, this means both these will be a prime ideals here, they will be proper prime ideals here. So, and the containment will remain containment. So, when I take the images of this in this B localized at P, it will be, usually we know it is denoted by P prime BP and P double prime P double BP, and this is contained in this. And now these are two prime ideals, because they were two prime ideals. These are prime ideals in B, therefore, the image under S inverse is also prime ideals, and containment happens. And where are they lying? So, they are lying over this maximal ideal. Just transfer the data to the localization. But now, this is a local ring, this is a prime ideal, this is a maximal ideal, and over this there are two of them which one contained in the other, they are lying over. But our earlier statement says that if you have a maximal ideal, then only maximal ideal can lie over the maximal ideal. Therefore, both of them cannot lie over the maximal ideals. So both of them are equal here. So that shows these are equal here, but then when we pull it back they will be equal here, and that is what it proves this statement. So this we have proved under we have proved statements under localization. What happens to the prime ideals? A prime ideal will go to a prime ideal under localization when it does not intersect with the multiplicatively closed set that we are considering, and it is one-to-one correspondence between the prime ideals who do not intersect with the multiplicatively closed set S and the prime ideals. So that proves that in the fiber of I star over P there can't be any containment relation between any two ideals in the any two prime ideals in the fiber. This is very useful fact. This I will use it to prove the lying over theorem. Now proof of lying over theorem. So we have given a situation like this: B contained in A. This is integral. This is our inclusion map, integral, and P is given to be prime ideal here. P is in the spec A, and we are looking for somebody here, P prime, and P prime should be in the prime ideal. This is what we are looking for. This is what we are looking for, and also it should lie over this. That means this P should be P prime intersection A. This is what we are looking for. Right? All right. So now what do I do? Again I do the same trick. We have given P. So given P in spec B, spec A, consider the diagram. So A is here, B is here, this is integral, then you go to A localized at P and go to B localized at P, where P is A minus P, not P, S. This is S, and we have this is S inverse B, and this is S inverse A. This is the S inverse of this inclusion map. This is inclusion map, and we know this is integral, and then we have checked that whenever I have integral homomorphism, then the S inverse of that is also integral. So this is also integral. And what are we looking for? We are looking for P prime here, which lies over P. This is what we are looking for. We are looking for this, which is lying over this. Well, but now I want to push this data to this localization. So that means what? I am looking for some prime ideal here which should not intersect with S, and that should lie over this PAP. So therefore, looking for Q, which is a prime ideal in S inverse B, with Q intersection this ring A localized at P should be PAP. Once you succeed in this is what we are looking for. Suppose you succeed in this, then what will you do? Then we will take then we will take P prime to be equal to Q, you pull it back to B, that is Q intersection B, and this will be the required one because that Q was here, you pull it back to P prime, and that one is equivalent to saying you pull it back here and then pull it back here. So, this Q is pulled back to PAP, and this one obviously when you pull it back you will get back your P. So, this one P prime has to go to P. So, that will finish the problem. And what did you achieve in this reduction? The achievement is this ideal here is not a prime ideal, but it is actually a maximal ideal. So, this proves, this means to solve the problem, to look for P prime, we may assume that the given P is a maximal ideal. That is the achievement. Alright, so now let us start once again with the assumption that P is actually the maximal ideal. Alright, so therefore we have the following situation. In B, this is integral over A, and M is a maximal ideal in A, and we are looking for M prime, because we know if at all there is a M prime, if at all there is a prime ideal, it has to be the maximal. So, in SPM B such that this is lying over this, that is this one is A intersection M prime. So, we are looking for this, with this condition. Alright, so what do we do? Alright. So, again I am going to localize again at M. So, consider the diagram. So, A is here, A localized at M is here. This is the localization map. So, S is now A minus M. This was B here, this here, this is integral, this is B localized at M, this is the iota map, this is also iota map, and this is the inclusion map I, this is I localization of this S I suffix M. We are in this situation, and what are we looking for? We are looking for now somebody here, some maximal ideal here which lies over this maximal ideal, right. So, we are looking for that. Alright. So, first of all note that this ring BM is this S inverse of B, and this has to be non-zero ring, because if it is 0 this will also be 0, but this is not a 0 ring. So, this is a non-zero ring, and now you extend this maximal ideal there. So, and M extended to this, if this is a proper ideal, then I will take any maximal ideal which contain this, and then that will, I will pull it back this, and that will be the maximal ideal here which will lie over this. actually we only need a prime ideal. So we don't even that is the consequence. So what you do is, first of all, so we claim that this is a proper ideal. Assuming the claim, what are you going to do? Now let um, m prime be, this is a proper ideal. So let m prime be a maximal ideal in B localized at M with M prime contains M localized at M. So if this is a proper ideal, I can always find a bigger ideal which is a maximal ideal in Bm, so that this contains this. And now this M prime has to, so here I have chosen my M prime. This M prime, when you contract it here, this is the way I have written it is, this will contract to M prime and then this has to contract to M only, because this way it is contracting to M. So I only have to prove this claim. Alright, if it is not equal, if it is equal, then what happens? So if M times Bm equal to Bm, that means what? That is 1 will belong to the other side, 1 which is actually 1 by 1 we should write, these belong to M times Bm. That means what? That means 1 I can write it as, so that is 1 I will write it as some A1 x1 plus an xn, where A1 to An they are in A and x1 to xn are in this M, and x1 to xn they are in the ring, they are in the ring B. So and these are the generators, so these are in fact they are in M. Because this ideal is generated by elements of M. So therefore I can write that in a combination, finite combination of the generating set. So this is the some elements in M and the combination is 1. Alright, so but what does this mean? What will this contradict? That means, so this means, so come back here, we have this situation, A is here, M was given here, B is here, and I found elements here, A1 to An and x1 to xn we found, such that now I take the subalgebra of B, A subalgebra of B generated by this. This is A subalgebra of B generated by A prime. Now this M which was already M B localized at M, this was a unit ideal, and that is because this equation. But that equation is also valid here. So when I localize here, that means M extended to A prime M prime M prime M equal to also A prime M, same equation, because that makes sense. So what is the achievement again? That means we may assume, and this is integral that we know. So we have proved that this one is also integral extension. This one over A is integral, and it is finite type. therefore finite. This we proved yesterday's lecture. This we proved yesterday. So this is a finite type, finite algebra. A prime is a finite A algebra. So that means it is a finitely generated a module, and then it satisfies this property. It already satisfies m times A prime equal to A prime, because this equation is there. But then Nakayama lemma says will imply A prime is 0 actually, a contradiction. So therefore, what we proved is this one cannot be equal, and therefore I can choose a maximal ideal, and then earlier proof goes on. So this proves that the map is surjective. Lying over theorem, we have proved it, and after the break we will see some more the third theorem of Cohen-Seidenberg, that is also very important, that is called the going up theorem. Thank you very much. We will meet after the break.